La 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 la.
Welcome to my classroom. In this lecture, we are going to discuss about flow measuring devices. So in chemical industries, it is important to know how much a fluid is flowing into a system or out of a system, because we have to maintain a particular volumetric flow rate. So to measure the volumetric flow rate, we have different type of flow measuring devices. For example, they can be classified as full bore meters, or insertion meters. When we say full bore meter, that particular device, that volumetric flow rate measuring device, is acting over all the fluid that is passing through a pipeline, let me say. Okay, so or if I say insertion meters, so it will only measure the velocity at particular point, so that the device is not acting on the complete fluid, but rather it takes into consideration as a particular element of liquid or particular layer of the liquid is being considered, where we insert the device to particular point in the complete cross-section area. So, but whereas this full bore meter will act over the entire fluid. So, the total kind of cross-section area of the fluid that is flowing is covered in case of a full bore meter, whereas in case of an insertion meter, only we measure the velocity at a particular point. Okay, so the device is not acting on the complete fluid. So, when we say that fluid is, when we say this fluid of this cross-section is flowing, when it is a full bore meter, the entire fluid will flow through this device. Okay, so this is our flow measuring device. So the entire fluid will flow through this full bore meter, whereas in case of insertion meter, so we will have this device only to a localized point within the cross section area. So only that particular layer of liquid is being entering into this insertion type of meters. Okay, so for example, piezometer is there. So pitot tubes are there. So such type of devices don't act on the complete fluid. So they are called as insertion meters. Okay. So this is one type of classification for FMD, that is flow measuring devices. And coming to the next, another type of classification is either it can be variable head meters. So there is going to be variation. There can be variable head meter, or it can be variable area meters. So when you say variable head meter and variable area meters, as I said, the head refers to pressure head, which means that there will be change in pressure with the change in the volumetric flow rate. It means that the cross-section area of this device, in comparison to the pipeline and the device, so the area will stay constant. Okay, so the area is constant, hence when there is a change in the volumetric flow rate, there will be change in the pressure drop. Okay, so the pressure drop will be measured. So the change in the pressure head, such devices are called as variable head meters. So variable head meters are the devices, full bore type of devices. Okay, so wherein the cross section area of the device remains constant, and with the change in the volumetric flow rate, there will be change in the pressure drop. Okay, so next, coming to variable area meters. So in case of variable area meters, so the cross section area of the flow measuring device will keep changing with respect to change in the volumetric flow rate, which means the pressure drop remains constant. So the delta P remains constant. Here delta P will be a function of volumetric flow rate. Here delta P is equal to constant. Okay, here area is constant, cross section area. So in this case, cross section area is constant. Okay, and the pressure drop will be a function of volumetric flow rate. Whereas in this case of variable area meters, the area will keep change. So cross section area will be a function of volumetric flow rate. Okay, so area will be a function of volumetric flow rate. That means that the cross section area through which the fluid is flowing will keep changing with respect to volumetric increase in the volumetric flow rate, whereas the pressure drop across the flow measuring device will be the same. So we are going to consider some cases like variable head meters, or type, as I said, they are coming under the full bore meters. That means the entire fluid will be flowing past this full bore meters. And for example, variable head meters, we have venturi meter, we have orifice meters. Okay, so these two are devices where the cross-section area is fixed. The area cross-section area of the orifice, cross-section area of the throat section in the venturi meter, they are all fixed. They don't change with the change in the volumetric flow rate. Whereas the pressure drop across the flow measuring device will keep changing with change in the volumetric flow rate, which will be made as a function of this thing. So that's where we come to know what is the volumetric flow rate. Okay, so that is variable head meters. Whereas in case of variable area meters, we have an example of rotometers. So the rotometers are again a variable head area flow measuring device. It is again a full bore meter, and in which the pressure drop will remain constant and the cross section area will keep changing with respect to the change in the volumetric flow rates. So in this lecture we are going to discuss in detail about rotometers. So we'll look into the construction, working principle, the equation, and we will derive an expression to find out the maximum volumetric, maximum velocity and the actual discharge through the rotometers. Ready? One of the examples for variable area meters is rotometer. A rotometer So rotometer is a flow measuring device. It is one of the type example for variable area meters, where the cross section area of the fluid flow will vary as a function of discharge, and the pressure drop across this will be the same. Okay, so pressure drop across the variable area meter will remain constant, whereas the cross section area through which the fluid is flowing will change with respect to the volumetric discharge, that is the actual discharge that is taking place. Okay, so a construction, if you look into the construction of a rotometer, it is usually made up of a tapered section. The tapered section means two different diameter at both ends, gradually variation. There is a gradual variation in the diameter from top to bottom. So usually a smaller diameter at the bottom and a larger diameter at the top is assumed. So it is usually made up of a glass tube. Yes, transparency is preferred in this. So it's usually made up of a transparent glass, or even it can be made up of plastics. Okay, so that way it will consist of a tapered glass section with a smaller diameter at the bottom and a larger diameter at the top. Okay, and this will consist of a throat So it's so we have a tapered glass which is connected to a frame. Okay. So in this tapered section, we have a float which is connected to this, and this is guided with some. So this will be connected to this helical groove. Okay. So this is called float. It is made up usually of a material which has a density higher than that of the fluid. So when I say liquid water, water has a density of 1000 kg per meter cube. Hence the float should have a density more than that. Okay. So similarly, if the gas is flowing, we can even use it as light as possible. Whichever having more than density of 2 can be used, because the air density is around 1.2 at normal conditions. You should have a flow material density of the float which is greater than density of the float should be greater than density of the fluid. Okay. So that is the condition selection criteria for this float material, and this float material usually have a diameter equal to that of the bottom diameter. There is a bottom area through which the fluid is flowing, and this float will rest when the velocity and the volumetric flow rate, because usually it is connected to the pipeline. Okay, so the fluid will be usually flowing from bottom to top. The fluid will be flowing from bottom to top, and what happens when there is no fluid flow, this float position will be at the zero level. Okay, zero in the sense actually this tapered section will be calibrated in such a way that according to the float position, because with increasing the volumetric flow rate, the float will take a position, because the fluid will push this fluid up. Okay, but so that way you have the fluid with its pressure, it will try to push the float up, but it will take a equilibrium position according to the volumetric flow rate, because there are three forces coming into picture here. We have drag force, we have buoyancy force, and we have weight force due to weight. Okay, so that way there are three forces we consider in taking a equilibrium position here, because the weight, the drag force is there, buoyancy force is there, and weight force is there. So these two, summation of buoyancy force plus summation of drag force, we know the drag force is along the fluid flow, is equal to force due to weight. Okay, weight force. Okay, so these three forces are coming into picture. At equilibrium, these two will be equal to this, and that will be the rest position, and that is corresponding to a particular volumetric flow rate. So we will have a scale, calibrated scale over this tapered glass itself, such that we will be able to readily measure the volumetric flow rate depending upon, because we are going to, let me say we have a valve here. Okay, so using the valve, we can adjust the volumetric flow rate. But what is the position and what is the volumetric flow rate? For example, liter per second, or it can be meter cube per hour. So whatever is the reading, we can measure it from the scale which is written readily, because it's a calibrated device, pre-calibrated. Before we use it, we have a calibrated scale over here. With the volumetric flow rate can be 0 to 20 liter per second. So you can have say 15, 10, 5, 2, 0 like that. Okay, so any scale, it should be in a proper scale, right? So 0, 5, 10, 15, 20 like that. We can have a scale. So we are going to have a calibrated scale, and this float will have, it's a visible plate, right? As I said, it's made up of glass or plastic. So when the float takes a position, according to the float upper end, we can say measure what is the liter per second or whatever unit it is given, scale is calibrated. Okay, so by adjusting the valve here, we are going to change the volumetric flow rate. When we are changing the volumetric flow rate, the float will move from bottom to top with increase in volumetric flow rate. When it is 0, it will be at the bottom position, and when it is fully open, it is going to be at the uppermost position. Okay, so and it's readily made. So the advantages of this type of rotometer device is it is simple in construction, and it gives a direct reading, no calculations involved. So even a supervisor with less technical knowledge also able to measure the volumetric flow rate. Okay, and this device is made simple one, and there are only three forces acting on this float. So we have buoyancy force, drag force, and weight force. When the sum of buoyancy force and drag force is balanced by the weight force, so that will be the equilibrium position. And for each volumetric flow rate, you are going to have a certain balance equilibrium position, and based on the equilibrium position of the float, we will get the direct reading of what is the volumetric flow rate. So it's one of the variable area meter. But where is how the flow is taking place? Why the name is rotometer? What is the area through which it is floating? Let us say, so it is the cross section at any position. This is the cross section area of the tapered glass, and you have a float diameter which is fixed. Okay, so this is the float material which has a density greater than that of the fluid. So float cross section area is fixed, but depending upon its position, the outer tapered section diameter will keep changing. So if you look at the top view, so the tapered cross section area will be changing. So actually where the flow is taking place, the flow of fluid is through an annular region. So it is an annular flow taking place between the float and the tapered glass. So outer diameter is, for example, this is my float position. Okay, this is my float position. So at this position there is a diameter for d outer, let me say, d of the tapered glass. Okay, so diameter is there and diameter of the float is there. Okay. So here to here it is diameter of the tapered pipe, and this is the diameter of the float. Okay, so this we have two diameters. One is diameter of the float. Okay, so diameter of the float and diameter of the tap. So diameter of the tapered glass, diameter of the glass. Let me say diameter of the float. So what is the area through which the fluid is flowing? It is this area minus this area, cross section area. We have to subtract the cross section area. So area of fluid flow. Area of fluid flow is, so where the fluid is flowing, it is pi by 4 into, let me say, d2 square minus d1 square, where d2 square is diameter of the cross section and d1 is diameter of the float. Okay, pi d square by 4 minus pi d1 square by 4. So we get the area of the fluid flow. So this is the area through which the fluid is flowing. Okay, and what is the maximum pressure drop? So the pressure drop will be maximum when based on its position. So when you have V equal to V max, we are going to get the what is the delta P. What is the delta P across this device? Maximum pressure drop across this device you will get when the velocity is maximum. Okay, so that we will derive the expression now. Okay. Now we know that there are three forces which are acting: buoyant force, drag force, and the force due to gravity. Okay. So what are these three forces? Let us say the float. So whatever is the shape of the float material has, the float material has a mass mf, volume occupied by the float is Vf. Then what is density of this float? Density is mf by Vf. So what is mf? Rho f into Vf. Okay, so that will be the mass of the float. Okay, now what is this buoyant force? So buoyant force is m into is the mass of the fluid which is replaced by the volume into g. Okay, so what is the mass of the fluid volume replaced is density of the fluid, because mass of the float is rho f Vf. Mass of the fluid replaced by it is density of the fluid into volume of the float into g. And similarly, what is gravity force? It is m into g. The gravity force on this float material is mf into g, which is rho f Vf into g. Rho f Vf into g. Rho of the float. Okay, V of the float and g. Okay, now what is the drag force? Ft, we know that it is half rho v square CD into area. Okay, of rho v square CDAP. Okay, so that is the projected area, or you can say the area through which it is flowing. Okay, so we have drag force equal to half rho v square CDA, FB equal to rho f v float into G, Fg equal to rho f float v float into G, where V is the volume of the float, density of the float. Okay, because we are writing mass in terms of density and volume. Okay, don't confuse with the velocity term here. So this Fd, when V is Vmax, we have Fd equal to half rho Vmax square into CD into A. Okay. So this drag force is on the area of the float it is happening. So you can say AF also. Okay. So I repeat, we have buoyancy force, which is mass of the fluid replaced by the float, into G, which is given by density of the fluid into volume of the float into G, and gravity force is mass of the float into G, which is density of the float into volume of the float into G, and Fd by definition we know that half rho v square CDAP, and Fd when velocity is maximum we have half rho v max square CDF. So substituting these three in this equation, that is at equilibrium, we know that at equilibrium this summation of buoyancy force and drag force is balanced by the gravity force. That's how it takes an equilibrium position when it depends upon the volumetric flow rate. At different volumetric flow rate, whatever is the force, all these things, we are going to have these terms. So substituting this, we are going to get expression, rearrange and write what is Vmax. Please do it yourself. So we have buoyancy force plus drag force is equal to gravity force. So we can say Fd equal to Fg minus Fb. Okay, what is Fg? It's a gravity force. So mass of the fluid, mass of the float into G minus mass of the fluid replaced into G. Okay, so this one is again mass of the float is rho f Vfg, and this one is rho of the fluid into volume of the float into G, because volume of the fluid displaced is equal to volume of the float, right? So that is the buoyancy Archimedes principle. So we have this. So we can say that Vfg can be taken common outside. So Vfg into rho f minus rho is equal to Fd. And Fd, what is Fd? We have Fd equal to Vmax square CD into area of the float. Okay. Now what is Vmax? Rearrange to write what is that. I repeat. So the buoyancy force plus drag force is equal to gravity force. What we are discussing here is we are having a float material. Okay. So there is a buoyancy force acting upwards, and there is a drag force which is again acting upwards, and we have gravity force which is acting downwards. So this is the force balance. So applying force balance, and at equilibrium we have Fd plus Fd equal to Fg. So if you take this Fb to the right hand side, you have Fd equal to Fg minus Fb. Okay, which is, and gravity force is mass of the float into gravity, acceleration due to gravity, minus buoyancy force is mass of the fluid displaced into acceleration due to gravity, and mass of the float can be written as density into volume of the float, and mass of the fluid replace this, again density of the fluid into volume of the fluid displaced, but you can say volume of the fluid displaced is equal to volume of the float. So we have rho into Vfg. Okay, so in this Vfg is common, so we have taken the Vf into G common outside, and we have what we have is rho f minus rho, and we have left hand side Fd definition is half rho V max square CDAF when V is V max. Okay, so we have an expression for V max by rearranging this. So this 2 will go to the right hand side. We have 2 Vfg into rho f minus rho by rho. Rho is going to the left hand side, and we have CDAF. Okay, so the CD is coefficient of drag, AF is the area of the float, and Vmax is equal to square root of this. Okay, so this is the expression for Vmax, and we know that from continuity equation for incompressible fluids, and we have Q equal to A into V. Okay, area of the, as I said, what is the area? Area is the float minus this. So this is our region. So we have this diameter, let me say D2. So we have D1 square minus D2 square. So that is our area of the annular region. So area of annular region into Vmax is the volumetric flow rate. So Q is equal to, Q theoretical is equal to that pi by 4 D1 square minus D2 square into Vmax. Okay, and again this is only a theoretical volumetric flow rate. If you want to get what is the actual volumetric flow rate is equal to coefficient of discharge into Q theoretical. Okay, so what you have is CD into Q theoretical. So we have CD into that pi by 4 D1 square minus D2 square into this Vmax. What is Vmax? We have square root of 2G Vf volume of float by CD A into area of the float. We have rho f minus rho by rho. Okay, so this is the expression for actual discharge. So this is the expression for actual discharge. I repeat, we have three forces acting on the drag floating material. One is buoyancy force, which acts along the fluid flow direction because it is trying to lift it, and we have drag force, which is along the fluid flow direction, gravity force, which acts downwards. So force balance, which gives Fg plus Fd equal to Fg, and substituting with their basic definitions of what is buoyancy force, what is gravity force, and drag force. And in drag force term, we substitute V equal to Vmax, and rearranging this, we are getting what is Vmax, and that Vmax we are substituting in what is Q theoretical, and again Q actual, we introduce the term coefficient of discharge. And for usually for rotometers, this coefficient of discharge is around 0.7. And actually, what is this? Or if you look at the cross section area and this thing, it is similar to an orifice. So what we can say, this rotometer is a variable orifice meter. Actually, orifice meter, you have an opening, that diameter is fixed. Okay, so here also we are having a float, and the outer diameter is varying with depending upon the position of the float. It is similar to a flow through some annular region. It's again similar to orifice, so it has a better coefficient of discharge than the orifice. So if, for example, orifice meters, we have very less coefficient of discharge, like less than 0.6. So it's going to have more than 0.7. For venturi meters, it is possible to get even very well calibrated venturi meters or new calibrated venturi meter. It can be even 0.9 coefficient of discharge. Okay, so that way the CD of a rotometer lies between the orifice meter and venturi meter. That is, you can say it is better than the orifice meter because the pressure drop is less than that is occurring there. Okay, so that way the different parameters we need to know are what is the position. Based on the position, we are going to have a diameter 1, we have diameter 2, which is the diameter of the float, and we have volume of the float, density of the float, density of the fluid, coefficient of drag, coefficient of discharge, area of the float. Okay, cross section area of the float. So this term constitutes the final expression for rotometer. So this is the final expression for a rotometer, and what we observe is the actual discharge is proportional to square root of rho f minus rho by rho. Okay, we can say that the discharge is a function of square root of rho f minus rho by rho, or you can say 1 minus okay. So Q is proportional to square root of rho f minus rho by rho, and now when there is a change in two different fluids are there, density 1 and density 2, and we want to maintain the same position. So what can be the what should be the discharge? What will be the discharge or the position can be determined. So based on the different fluids, density 1 and density 2, you can find out what is the discharge. Okay, that is one thing. Another thing we should know is what will be the position for a fixed flow rate. Okay, for example, let H be the total height of this rotometer. Okay, so let H be the total height of the meter, and what is the diameter at any particular distance x? Because we have diameter at the top, we have diameter at the bottom, right? So we have a diameter at the top and diameter at the bottom. So what will be the diameter at a distance of x? How you get it? So diameter of a distance of x is equal to, so the diameter at the bottom plus, so we are going to find the what will be the diameter at this distance x. So diameter at the bottom plus diameter at the top minus diameter at the bottom into x by h. So this is the equation we used to find what will be the diameter at a particular distance of x. For example, what will be the distance? For example, this is 75 mm and this is 150 mm. What will be the diameter? Let it be 1 meter's height. Okay, so what will be the diameter at exactly 0.5 meters? That is, or 500 centimeters. So at 0.5 meters, what will be the diameter? Can we find out? So it is 75 mm plus 150 minus 75 by 75 divided by total height is 1 meters. Okay, so these are in mm. Okay, so this is in mm. Okay, anyhow this is will get cancelled. I am substituting 0.5 by 1. Okay, so it's going to be 150 minus 75, it is 75, and it is 0.5. 75 by 2 plus 75. How much? So 75 by 2 is 37.5. So the diameter and the x equal to 0.5 meters is 75 plus 37.5. How much? 112.5. Is that right? 0.5. Okay, so that is what? Obviously, it is between 75 and 150 mm. Okay, so between 75 and 150 mm, so we are going to have a diameter at any particular distance. So this is only for understanding. But advantage with this rotometer is we don't need to do any calculation when we are using this type of flow measuring device. We have a calibrated scale. So this using these relations or these equations at a particular height, what is the diameter, and at the diameter whatever is the velocity. Based on that we are going to fix. We are going to see, for example, if it is in this one we are going to have a calibrations. Okay, so the calibrations are based on these equations. So we are going to get a ready-made value determination of volumetric flow rate whenever we are using this type of rotometer. So it's simple in construction and it is relatively cheaper and it is more accurate and it can be used for both liquids as well as gases. So that's what in our fluid particle mechanics laboratory, when in a packed bed experiment or any flow through fluidized bed using water or even using air, wherever we have used these rotometers. I hope you might be adjusting a knob to fix the floating position to fix the flow rate. Okay, so by changing the knob valve, by opening the valve position into different positions or bypass valve positions, So we will be fixing the volumetric flow rate at which the fluid is flowing. So that way it is used for both liquid as well as the gases. Okay, so that is one of the important variable area flow measuring device which is called as rotometer. There is a question why it is called as rotometer. Actually, there are some grave in the float material. Say for example, if this is the float material, so there will be some cravings are done on it. So based on that, so the fluid to maintain to avoid tilting, the rotometer is made to rotate. Okay, so that way it is called as rotometer. Why it is called rotometer? In the float surfaces, some markings are done such that when there is a fluid flow, to avoid the tilting, it will keep rotating. So that's why it is called as a rotometer. Okay. Another thing is, and to maintain this float into single position, usually guiding guiding pipe will be there, so over which the float will move only up and down. Okay, so that way that is guiding line is there. Okay, so that also present in the rotometer. Okay, that's all about a rotometer. You should be able to list out what is the working principle, what is the expression, final expression to determine the actual discharge, advantages and limitations of this rotometer. Okay. Remember, this can be used to measure a wide range of volumetric flow rate. It can be used for various fluids, regardless of the different viscosity or density, and it is used even for compressible as well as incompressible fluids. So that's why I was telling you, it can be used for liquids as well as for gases or vapors. Okay, but only thing is we have to ensure that the float material is of corrosion resistance. That's why it is usually made up of stainless steel. It can be even made up of ceramics. Okay, it can be made up of bronze, monel, a kind of aluminium, like that. Different type of floating materials is preferred depending upon the fluid which we are using. Okay, so that is the one advantage, but only limitation is that float material may need to be replaced if it is undergoing corrosion. Okay, so if corrosion preventive material is preferred, chosen, in that case that problem can be addressed. So one more thing to note down is, so we have seen that Q is proportional to square root of rho F minus rho by rho, right? So Q is proportional to rho F minus rho by rho, but when you consider gases, actually for gases, what happens? Gas density of gases is very much less than density of the float material. So we can say rho F is very much greater than rho. So in this term, you can say that Q is proportional to rho F by rho. Okay, this is for gases. Okay, so when it's proportional to rho F by rho, and in CPC course, you might have seen that what is density of a gas mixture? Density of a gas mixture is equal to Pm by RT. Right, where M average is there coming into picture, or you can say rho is proportional to M average. Okay, so when I say that, we can say that density, when you know the molecular weight of the float or molecular weight of this fluid, we can even write this thing that Q is proportional to MF by M of the fluid. Okay. Now, when you have two different fluids, if you know the molecular weights are different, for example, Q can be written as, let me say Q1 is proportional to rho F by rho 1, and let me say there is another discharge corresponding to rho F by rho 2. Then what is Q2 by Q1? Q2 by Q1 equal to, Q2 is inversely proportional to rho 2, okay, and Q1 is inversely proportional to rho 1. So you have Q2 by Q1 equal to square root of rho 1 by rho 2. Okay, so then you can say that Q2 by Q1 is proportional to, not equal to. Okay, so Q2 by Q1 is proportional to rho 1 by rho 2, and rho 1 is proportional to M1 M2. So we can say that Q2 by Q1 equal to average molecular weight of fluid 1 by average molecular weight of fluid 2. Or if it is pure element, it is not average, it is simple molecular weight. So we can say that ρ1 by ρ2 is proportional to m1 by m2, where m is the molecular weight. So the type of questions are repeatedly asked in the competitive exams like GATE questions. So you should be able to know the final expressions, mainly this proportionality, that Q is proportional to ρf minus ρ by ρ for rotometer. Okay, this is for this rotometer we are discussing. Okay, so inside a rotometer, and particularly for gases, this term is negligible because gas density is very much less than the solid density. So ρf is very much greater than ρ. So we have Q is proportional to ρf by ρ, and we know that density is Pm by RT, so density is proportional to M average. So when you have a fluid 1, then we have two different fluids. Okay, so fluid 1 and 2, we have square root of ρf by ρ1, square root of ρf by ρ2. This is actually gases. Okay, two different gases, gas 1, gas 2. Then we have Q2 by Q1 equal to square root of ρ1 by ρ2. Then we have Q2 by Q1 equal to square root of M average 1 by M average 2. So such type of numericals can be expected in the competitive exams or even for our examinations. Okay. Now we will solve few numericals based on these rotometer concepts that we have learned. Please take down the problem. So we have a rotometer through which air is flowing. Okay, so we have a rotometer through which air is flowing, and we have a particular height h. Let me say at a particular height h, there is a location, let me say x. Okay, and the location is x, that is float will be at a particular position, right? So with this position, the volumetric flow rate of air is found to be 300 cc per second. That is cubic centimeter per second. Cc means centimeter cube per second. Okay. Air has a molecular weight of 28.8 kg per meter cube. So we have a rotometer in which air is flowing with the position of float being at some distance x from the bottom. Okay, and the volumetric flow rate is 300 centimeter cube per second. It can be any value. Okay, so you can even do for 100 centimeter cube per second or what. So that's not the point here. The point here is when the same rotometer is used to pass another fluid, let me say helium. Okay, same rotometer we used to pass helium over it. We know that helium will have a molecular weight of around 4 kg per meter cube. So here helium with a molecular weight of 4 kg per meter cube is passing through the same, and we want to have a float to be at the same position of h or h distance from the bottom. Okay. Okay, so we have the position, same position, that is float is to be at the same distance when this volumetric flow rate of air was 300 cc per second. So here also the same position, but when the fluid have a different molecular weight, right? So air has a molecular weight of 28, helium has having a molecular weight of 4. So what will be the Q? Find Q of helium when the float is same position. So when the helium is flowing through the same rotometer with same float position, what will be the volumetric flow rate? Do you think it will be the same? When the density of the fluid is different, float position is to be supposed to change for same volumetric flow rate, or it will be the same for different layer of densities. So for that we should recall what we know about Q. We know that Q is proportional to, this both are gases, air as well as helium. So we know that Q is proportional to ρf minus ρ by ρ, or you can say for gases, this ρf is very much greater than ρ. So we have ρ proportional to rho F by rho, or you can say Q is inversely proportional to rho. Okay, so you can say Q square is proportional to 1 by rho. So we have Q2 square is proportional to 1 by rho 2 square, or you can say Q1 square is proportional to 1 by rho 1. So what is Q2 square by Q1 square? So what is Q2 square by Q1 square equal to? Q2 square by Q1 square is equal to, Q2 square is 1 by rho 1. So Q2 square is 1 by rho 2, then Q1 square will become rho 1. Or you can say Q2 square is equal to Q1 square into rho 1 by rho 2. Okay. And we know that I explained earlier also rho is proportional to m. So what we can write is, because we know that rho equal to Pm by RT. Okay, so that way rho is proportional to m. So what we can write is Q2 square is equal to Q1 square into m1 by m2. And we know the molecular weights 28.8 and 4, and Q1 is given as 300 cc per second. So Q2 square can be calculated. So then what is Q1? Okay, so it's a straightforward substitution. Q1 square is 300 cc per second. Again convert to meter cube per second. Okay, so molecular weight is kg per meter cube, kg per meter cube. Substitute that one to get what is Q2. Okay, please comment what is the value of Q2. All of you. So here what we should know is how from Vmax equation and Q actual, what we have is Q is proportional to square root of rho F minus rho by rho, and for it is when the fluid is gases, the F here refers to float. Okay, so that we should know. Density of the float is a solid material and this is gas, so rho F is very much greater than rho. That's why we get Q is proportional to rho F by rho, or you can say Q square is equal to rho F by rho. Okay, so even we should write like this only. Rho F is same, that's why when we take ratio, it simplifies to rho 1 by rho 2. Okay, rho F gets cancelled. Okay, now please correct that. And the answer is going to Q2 square is equal to Q1 square into m1 by m2. Therefore, Q2 is equal to square root of that. And whatever is the in meter cube per second, please report. Okay. Or even if you want to keep it in centimeter cube per second, you are going to get in centimeter cube per second. When you convert to SI unit, you will get in SI units. Okay, because it's only a mere ratio. You can even keep them in same ratio, but these two should be in same ratio. One should be in kg per meter cube, means both should be in kg per meter cube. One in kg per meter cube, one in gram per cc, we cannot substitute. Okay, so please report the value. Please comment what is the value of Q2. Please take down the problem. Consider a rotometer of 300 mm. Consider a rotometer of 300 mm length, that is 30 centimeters length, with a bottom diameter of 20 mm, with a diameter at the bottom being 20 mm. You know that rotometer is a tapered section. So here at the bottom, the cross-section area we have to find. So that in that place the diameter is 20 mm and the total height is given 300 mm, that is 30 centimeters, and diameter at the top is given 25 mm. So diameter of the bottom is given as 20 mm. Diameter of the top of the rotometer is 25 mm. And the height of the rotometer is given 30 centimeters, that is 300 mm. Okay. And coefficient of discharge is given as 0.7. Coefficient of drag is given as 0.7. And density of the floor. So we have a floor material with a density of 4,800 kg per meter cube. Remember, it can be given in the form of specific gravity as 4.8. Specific gravity 4.8 or density of the floor material as per floor. Density of the floor is 4,800 kg per meter cube, and density of water is given as 1000 kg per meter cube. Okay, so that is 1000 kg per meter cube. And the volume of the floor, the volume occupied by the floor is given as 6 centimeter cube. So 6 into 10 to the minus 6 meter cube. Okay, so these are the given data. Okay, so now the question is, what is the mass flow rate when the float is at its half weight? So what will be the mass flow rate, m dot? Question is, find the m dot when the float is at middle portion. Half way means its total height is 300 mm. So what will be the float position when the float position is 150 mm? That is what the question is. Okay. So when the float is at its half way, that is in the middle of this rotometer, so what will be the mass flow rate is the question here. Remember, in actual equipment there will be calibrated scale. Directly we are going to get the volumetric flow rate. Now, so just to understand the derivation that we have done, so this numerical we are solving. So here I repeat, what is given here is we are considering a rotometer of 300 mm height, and it has a bottom diameter of 20 mm and top diameter of 25 mm. So question here is, what is the flow rate when the float is at middle or the float is at its half weight? The question here is, determine the mass flow rate when the float is in the middle of the rotometer or the float is at its half weight. Okay. So now, why this data is given is, we should know what is the annular flow, right? This annular flow. In this annular flow, what is the cross-section area? So that we have to know. So for that we should know pi by 4 d of the diameter of the tube at this location minus diameter of the flow square. Okay. So what is the diameter at a particular location x? Okay. So it is half weight is given. So what it is given that x equal to half of 300 mm. Okay. So x equal to around 150 mm. Okay. When x equal to 150 mm, what is the diameter of this x? So diameter of this x is, we have seen that diameter of the x equal to, any position x equal to diameter of the bottom plus diameter of the top minus diameter of the bottom into x by h. Okay. So we can calculate what is the diameter of this x distance away from this. So it is given it is half way. So we have half of its way is 150 mm. So when x equal to 150 mm, what is the diameter at this point? Okay, so it should be between 20 and 25. Easily I can say that the middle is going to 22.5. I am giving you other than this, what if it is given as 2/3 division, 1/3 division, for the purpose I am writing this formula. Right now we can calculate that it is going to be 22.5, but how we are arriving at it in this formula is like 20 plus 25 minus 20 into x is 150 by 300. Okay, so we have 20 plus 2.5 and this 5 into 1 by 2. 5 into 1 by 2 is 2.5. So we get 20 plus 2.5, which is 22.5. Okay, so we have 22.5, we are able to get what is the annular flow. Okay, so now how to solve this only preparation. So how to find the annular area. But how do we get this mass flow rate? How do we get this mass flow rate? So we have the formula, what is Vmax. Okay, Vmax equal to square root of 2GBF by CDAF into rho F minus rho by rho, right? So using this, we will substitute to get what is the velocity maximum. So for this all data we have, okay, 2 into 9.81 into volume of the float is given 6 into 10 power minus 6 into what is rho F minus rho by rho. We have rho F is 4800, rho is 1000, then we have rho, so that we can even determine separately what is rho F minus rho by rho is equal to 4800 minus 1000 by 1000. So what we get is 3800 by 1000, it is 3.8. Okay, so we have 3.8 as this value. And what is CD value given? CD is given 0.7. Even if it is not given, you can take the position of that for our Rotometer. And area of the float we have to calculate because we have the diameter of the float. Diameter of the bottom is 20 mm, which means the diameter of the float is also mm, because we know that the float diameter will be equal to the diameter of the bottom. Okay, so that way, what is the area of the float? We can calculate area of the float is equal to 5 by 4 into 20 mm, so 20 into 10 power minus 3 square. So from this we get AF value also. Substitute AF value and this we will get Vmax. So all of you please comment the answer what is your Vmax, because we will find the AF. So then we will substitute what is substitute this here and report what is Vmax value. Please comment here what is Vmax value. So after finding Vmax value, it's a matter of time to find out what is the actual discharge, because we know that actual discharge is equal to coefficient of discharge into area of this annular region into Vmax. Okay. So CD value is given 0.7. Area of annular I told you to calculate 5 by 4 d at x. The diameter is now 22.5 whole square minus 20 square into 10 power minus 4. You will get the area of annular area through which the flow is there. Okay, so the annular area of the annulus is you can calculate. Vmax you can calculate and report what is meter cube per second. Okay, so report also discharge in meter cube per second. Okay, so after finding this Vmax, we will substitute Vmax here. Area of the annular flow you will find out. Then how to get the Vmax? M dot. You know that M dot equal to rho into Q. What is this rho? The density of the fluid. Don't substitute the density of the float. Okay. So here we have to substitute density of the fluid into this. So we will substitute the density of water into Q. What you are finding out. So what you will get is 20 per second. So please comment what is Vmax value, what is Q actual value, and what is M dot value. So what we have done in this problem? First it was given that the bottom diameter is given, upper diameter is given, volume of the float is given. Okay. So we have taken the diameter of the float to be diameter of the bottom, and we have the density of the fluid is known. So first what we find is it is asked what is the mass flow rate when the float is at its middle position, right? So when the float is at its middle position, that is halfway of its between top and bottom, the diameter is going to be half of means what 20 is there, so it's going to be 22.5 mm. So from that we calculated what is the annular flow to this gap between, and the diameter is 22.5, diameter of the float is 20. So between that region, what is the flow that can take place? Cross-section area for that is determined. So what is after that we substitute we find out what is Vmax using the formula, because density of the float is known, density of the fluid is known. CD is taken, area of the float can be calculated by taking bottom diameter of the rotometer and the diameter of the float. We get the AF value. Substituting it, we get what is Vmax. We substitute Vmax value in the actual discharge. Then we substitute actual discharge in the entire formula to get what is the mass flow rate, and the position of the float is at middle of between the airborne section. So the same can be repeated when the position of the float is 1/3 of the one or 2/3 of the from the bottom. So that way you can try to practice these movements. Okay. 3, 2, 1. Well, if you visit our fluid and particle mechanics laboratory in our ground floor, or if you are from different college, in your college you may be having fluid and particle mechanics laboratory, there you will see that there are several equipments to which a rotometer is attached. So for example, if this is a pressure drop through a packed bed, you can see a rotometer of big size is attached to it to measure the volumetric flow rate of water. So this is a pressure drop equipment. It is one of the old setup. So you can see the big size rotometer is attached. And if you look at the new experimental setup, fixed and fluidized bed setup, in which we have 3 different particle sizes. For each packed bed we have a rotometer attached to it. You can see that it is a transparent glass with a float in between, and there is a tapering section with a varying diameter. At bottom to top there is a scale, calibrated scale. In the left hand side it is in the units of liters per minute, and we have in the right hand side the unit is changing in different units. Okay, so it's a ready-made reading you can take based on the float position. So this is a well calibrated equipment, straightforward, simple in construction, and the reading is simple, no calculations are involved in this one. So this is the setup of fixed and fluidized bed particle equipment. And if you look at another experimental setup, hydrodynamics of packed bed apparatus, which we have procured recently. So we have a packed bed, and you can see there is a rotometer attached to it. So these rotometers, there are 2 rotometers available here. One is for water, which will measure the liters per minute of water in 3 to 30 LPM, and we have for measuring the LPM of air, we have a rotometer attached to it. So that way this rotometer can be used to measure the volumetric flow rate of both liquids as well as gases and gas mixtures. And a principle which we have discussed, I hope it might have given you the understanding that there are only 3 forces acting on the float. One is the drag force, buoyancy force, and the weight force. So there is another, this is a research project equipment setup. You can see for measuring the air flow rate, or even for measuring the other things, we are having this thing. And this is the experimental video where when you are operating the equipments, you can see that float is moving from lower position to upper position as we are opening the valve. When the volumetric flow rate is adjusted, you can see that the float position is there. Say for example, right now we kept the valve position such that we have a LPM changing from 300, or now we are increasing it by opening the valve. It is increasing to 500 LPM. So we can again reduce it by closing the valve. Again the float position, you can see it is moving down from 8 LPM to down. So the readings in the right hand side is liters per hour. So usually we maintain LPM, so we vary from 2 LPM, 4 LPM, 6 LPM and 8 LPM, like that. So easily you can adjust the volumetric flow rate using this rotometer. So this rotometer gives a straightforward reading of what is the volumetric flow rate inside this. So it is a full bore meter. That means all the fluid is passing through the this full bore meter. Okay, it's a variable area meter where the pressure drop is constant, but with change in the volumetric flow rate, there is change in the cross section area through which the fluid is flowing. And there are, other than these flow meters which we have shown you for rotometers, there are other type of examples of different sizes is there. Apart from that, you can even attach a scale with like this, like a clock type can be made. So calibration is done such that with small changes we will have more deflections. Okay, so that way type of flow measuring device of full bore meters are also there. It is, as I said, it's a variable area meter. If you turn this back side, you have a rotometer actually connected to this. So there will be deflection. So what we have done is here the opening is done such that you can see the float material moving up and down. So you will be moving it up. As he is moving it up and down, you can see there is deflection in the scale calibrated. It's like a speedometer what we see in our car or two-wheeler. So when the float position is changing,
we have change in the volumetric flow rate, which we can readily read through the scale attached, calibrated scale attached to it. Okay.
Well, in this lecture, we have discussed about rotometer. We have seen the difference between variable head meters and variable area meters. And for under the variable area meters, we have discussed in detail about rotometer, its construction, the principle, and we have seen using the force balance. We have derived an expression for Vmax and how to determine the Q discharge, actual discharge. And we have also seen how its discharge will vary as a function of density or even as a function of molecular weight. And we have solved a few numericals also. Thank you so much for joining my classroom. Meet you with another lecture video. Bye-bye.
La 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 la. 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 La 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 la.